That's if you can actually use something like a biocoke or a charcoal that you've upgraded, like you can get hotter and you can get some functionality here and you can use it as a solid fuel. But again, there's an extra processing step. That's what's required. Biomass always has a competition with food issue. We just can't be cavalier about that. Land is land and it's valuable. There is no marginal land anywhere. Sustainability is an issue in terms of monocultures and their effect on biodiversity and all these things. I'm not hating, I'm just saying these are things you need to be clear on. And of course, there's geographic limits to how much biomass you can grow and how much biomass you can use. We think that the killer apps here are actually in stuff like steel, where you can use it as a solid fuel, and a cement where you can use it as a solid fuel. And that will complement nicely with hydrogen, which you can use as a gaseous fuel. In some chemical applications, it probably makes sense. Electrification, absolutely worth considering, especially for something like electrical production of steam. There's a lot of steam in these facilities, and you can make high temperature steam through electrification. Enormous amounts of zero carbon energy are needed, though. Easily a factor of 2 times to 5 times more electricity than the equivalent energy for fossil. You actually have to just put a bunch more energy in. And the build out for this in terms of the volumes and numbers is very, very large. Of course, the carbon footprint's also an issue. Today, grid ain't zero. Someday it will be, but for now it ain't. And so if you want to actually keep your eyes on carbon, you have to be thinking about a zero carbon source. So either hydro or intermittent renewables or nuclear will do the job. But typically a lot of the zero carbon electricity that's out there has a low capacity factor, which runs counter to how these facilities work. Almost all new generation going into this application has got to be firm. And that's hard. It's not done, it's not over, but it's hard. You have to be clear-eyed about that. Generally speaking, costs are pretty expensive. Yes, the costs are coming down. I was just in Saudi Arabia last week. They've just put out a 1.5 cent per kilowatt hour massive solar plant. And it's got a 70% capacity factor because it's balanced with wind. Like, that's really good. Like, we're coming down and that's helpful. Are we there yet everywhere? No. So we just, again, got to be clear-eyed about it. The big problem or the big challenge with electrification is actually the case for the innovation agenda that goes with it. The real question is heat deposition. How do you get the heat into the system? So you cannot retrofit a cement kiln with electrical heating. It just doesn't work. Like, how do you get the heat into it? Same thing with a blast furnace. How do you get the heat into a blast furnace? Deposition of heat is a challenge. You could replace the whole thing with a new system that has even higher capital costs because now the competition is for teardown cost as opposed to price parity. There are interesting ideas for novel reactors, especially ones beyond steam. So you can imagine an electrical ethylene cracker. Nobody's designed one or built one, but you can imagine it. And so there's, again, a case for an innovation agenda. A key technical challenge is overpotential. Overpotential is just how much extra electricity you have to put in to do the same thing. Especially for these novel reactors, you want to drop the overpotential hard. That's a research program. We should get on with it. So unsurprisingly, for those who track this closely, but surprisingly for a lot of other people, electrification of this stuff means a lot of extra infrastructure. You need transmission bus bars, you need high voltage lines, you need to move the electricity into places where it isn't happening today. A lot of that's local and regionally challenged. In addition to that, the system generation issues end up being important, as we've already discussed. Last on the technical pathways here is just carbon capture and storage. The nice thing about the carbon footprint here is that you can tackle both the heat and the byproduct process emissions. So for example, from cement calcining or from coke reduction in steelmaking, you can actually capture those emissions well, so you're not just getting heat, you can also get the rest of the balance of plant. We should all be grateful that we can put CO2 in the geosphere. That's where it came from. We got to send it back to the geosphere, and it stays when you do that. We understand that part pretty well. We do need to make sure that we manage upstream emissions in that process, of course, because if you're doing carbon capture and storage, there's probably some upstream emissions that it's very real in that, and if you want to care about the carbon footprint, you have to be serious about those upstream emissions as well. Cost for carbon capture and storage, and this was part of the finding of our report, yeah, it costs more. In many applications, it costs less than everything else. It's actually cheaper to slap an enormous plastic bag over a power plant and capture the CO2 than it is to actually do the other stuff we were talking about. It is, however, limited by stuff like the geology. If you don't have a CO2 storage site, you got nothing. You can't do this process there. There are also interesting opportunities to do stuff like reduce the cost of carbon capture further by integrating with heat recovery. There's a lot of heat in a steel mill. You can use some of that to recover a solvent. Maybe that's of interest. Has that been worked by anybody? No, there's almost no literature on there on these kinds of systems because people have been focused on the power sector instead of the industrial sector. That may reduce cost. It would also increase complexity, which is a challenge. Post-combustion capture can come in pretty much anywhere. Like that's pretty helpful. Other capture options may be better. So for example, for cement processes, maybe a calcium looping technology might be more helpful. Too early to tell, but again, an innovation agenda here is welcome. The key constraint here is really, do you have the geology? One last constraint, and this is something which we think is important from a sectoral position, in something like a chemical plant or a refinery, there are often hundreds of distributed point sources. Capturing from that is not trivial. It really isn't. So if you want to get to zero, if net zero is the goal, doing post-combustion capture on an entire chemical facility is perhaps not the way to go. You may be better served by some other pathway. A quick hit on the sectors, and then I'm going to turn it back to David. So let's talk about cement. Cement is about 6% of global emissions. Just heat from cement is about 2% of global emissions. If you want to get to zero, you got to get this. The heat mostly goes into two places. The rotary kiln, most people are familiar with, that's mostly solid fuel dumped in the top. And by solid fuel, I mean like anything. Tires, trash, coal, pet coke, you name it, they just throw stuff into the kiln. Also, a lot of heat goes into the preheating and pre-calcining units. So that's a place where actually you could potentially do some fuel switching more simply. One of the things that's important here is there is a really, really big process emissions with this. And one of the findings from the report is the only way you can get the process emissions is with carbon storage. You just can't get them another way. This gives you a sense of what the different options look like just from a carbon perspective, just from greenhouse gas emissions reduction. This doesn't cost. This is just, if you wanted to get the tons, how could you do it? And one of the things you learned is if you did hydrogen today, you'd increase your footprint. So you have to do blue hydrogen or green hydrogen to reduce the footprint. Same thing with renewables. If you just pull power off the grid, the footprint goes up. If you did zero carbon electricity for everything, the footprint goes down. Our best options for the cement industry were CCS on the whole system and a mix of biogas, both solid and liquid. Or solid and gaseous, I should say. It's important to note there are other decarbonization options. There's other things you can do to reduce the emissions. Clinker substitution, dematerialization, efficiency improvements, alternative binders, these novel cements like Solidia or Carbon Cure, novel processes like Calyx. There's other things that you can do. But if you want to go after industrial heat, we think that CCS and biomass are probably the easy ways to go. Iron and steel, about 5% of global emissions, about 2.5% of that is heat. Very hot, continuous operations, as we've said. You're looking at blast furnaces and basic oxygen furnaces. That's the primary heat load. In addition to that, there's small, substantial heat loads and stuff like the lime kiln, the coking, the sintering plant. Those are non-negligible. If you want to get to zero, you have to think seriously about those as well. If you wanted to do DRI, then actually you need to put heat into the hydrogen plant. So that's also a source of heat management. Right now, pretty much it's solid fuels, almost entirely coal and coke. Important in this, the chemical reductant, the coke, also provides heat, also provides structure in the melt. It has a bunch of physical and chemical attributes beyond heat production that are very, very hard to substitute in an existing unit. So, what can you do? We think, again, good option, CCS on the whole system. We have also begun to explore what's called biocoke. The literature out there is pretty limited, but there's been attempts to run steel mills on biomass, and in fact there are people who've tried to make biocoke. And this is something actually that Colin is particularly deep on. I look forward to his comments soon. One of the challenges with that is that the heat content of the biocoke is substantially less than the heat content of regular coke. So, again, another challenge. There's no shortage of those. There is already some people putting hydrogen into steel plants. I already mentioned the Alreata plant, which is sort of a direct reduction of iron, but Nippon Steel in Japan unsurprising for the Japanese. They've been running a steel plant on hydrogen. I also mentioned already the ThyssenKrupp pilot. There's people trying to do these things. And again, there are other options for decarbonization. Efficiency, modifying the coking process, putting more electric arc furnaces out there and coupling those with DRI plants. Like, there's ways to think about doing this. And of course, there's these novel processes like Boston Metal out there that may someday be able to provide something worth doing. I want to make a quick aside here. In the case of both cement and steel, efficiency is a thing to chase. It's important to know that the industries have done a very good job of efficiency over the past 40 years. Over the past 40 years, both of those industries have improved their efficiency 60%. So there's not a lot of low-hanging fruit in there, but there are unquestionably things to be done. Chemicals. 3% of global emissions, but again, half of that's heat. It comes from lots of stuff, though. Burners, boilers, furnaces, the special reactors like catalytic crackers and so forth. And they are distributed across the facilities. Right now, almost all of that heat comes from natural gas because natural gas is a feedstock in the plants as well. In some cases, they use LPGs. In some cases, they use liquid fuels to provide the heat. That is very common, for example, in the Middle East, where they have more oil than they know what to do with, and they just burn it for heat. In some developing countries, most notably India and China, they use coal to provide that heat, even in the chemical plants. And they also use coal as the feedstock for hydrogen to go into the chemical plants. So what can you do? We took a look at two subsets of the chemical industry. The chemical industry is, of course, thousands of products, all kinds of facilities. We said we got to focus our attention. Let's look at ammonia and let's look at methanol as two representative examples. So right now, ammonia, mostly the heat comes from the synthesis reactor and the steam methane reformer. Like, those are the heat producing or heat requiring units in the system. There's other small stuff, but you have to put a lot of heat in to make ammonia. Almost all of that comes from natural gas today. For methanol, again, the SMR or a gasifier is the source of heat. The methanol synthesis unit uses a lot of heat. And here again, you've got basically a series of catalysts, and you're running the gases over hot catalysts, and it's just required to make it work. Also, distillation columns require some heat as well, and the small boilers and so forth. Today, again, almost entirely gaseous fuels. We see the best options here is hydrogen. We can start with blue hydrogen today and move on to green hydrogen as that gets cheaper and scaled up. Again, developing that aquaculture. Today, we can also start with biogas where we've got it, biomethane where we can make it from, say, an anaerobic digester or something like that. If we have that, this is a really good application for it, as opposed to, say, just burning it in a turbine. Maybe it's better off to use the scarce biomass resources we have to decarbonize these hard to decarbonize sectors. We can do partial electrification in these sites. So there's a lot of boilers in these facilities. There's a lot of steam units in these facilities. Those are places to explore what's going on. Today, that would basically double the cost for steam production. Okay, well, that's a place to start. Other decarbonization options, efficiency. Here there is larger opportunities to think about efficiency. Steel and cement have done a pretty good job on efficiency. There's farther to go in these kinds of facilities. And of course, there's novel processes to explore. In thinking about how to take all of this forward, we really think of innovation as a critical component. We just need to start working on this stuff and coming up with better ideas. First order of business, what are the trade-offs? It's easy to think of a novel thing, but at the end of the day, like, these are pretty complicated. You're buying and selling one thing in another place. What are you doing? So power to gas, renewable hydrogen end up being important. What methods of electrification are there and how do they really work? And then new approaches like zero carbon industrial gas production, industrial heat storage, new electrification technologies, all worth exploring. Other issues is if hydrogen is going to be big, we need to be thinking about hydrogen in a new way. How about time-phased in options, combining CCS with efficiency and novel kinds of fuels? Can we use hydrogen and biomass and partial substitution today for remote facilities? Can we ship hydrogen to them? This is something both the Japanese and the Norwegians are busily working away on. We'd like to see more of that. Can you do partial electrification? Do some of that stuff today and then combine that with, say, hydrogen or biomass to get full decarbonization of the process heat? You know, we got to see what we can do. There's almost no analytical tool out there there's also almost no data out there. This data is not captured. So an important component of an innovation agenda is to just actually start gathering the information you need to start doing good analysis. We found that extremely hard to find. Oh, and one last thing on here. At the end of the day, it may be that the cheapest way to decarbonize this stuff is just do direct air capture somewhere else. If it ends up costing $600 a ton to decarbonize these things, direct air capture is already cheaper than that today and the costs are going down. It may be that the way to go after these tons is by sweeping up the mess afterwards. That may not be ideal, that may not be preferred, but it may actually be the cost competitive arrangement. One of the takeaways from this is that CCS is probably going to be important one way or another in this facility, either for hydrogen or for post-combustion capture or for direct air capture. It's going to be one of those things that is part of the solution set in this arena. With that, I'm happy to turn the floor back to David. As you wish, sir.
Thank you, Julio. Let's talk about policy, because this agenda will not move forward at the pace required, or maybe at all, without policy support. So we offered, I think, 8 policy options in the roadmap. First is government support for R&D, just detailed different R&D directions that we recommend. That needs resources. U.S. Department of Energy, our national lab system, is a great place to do this. We have tremendous expertise that needs the funding, needs the policy direction in order for this to receive priority. Other governments around the world have this capability too. This could be part of the mission innovation agenda. Government R&D is really important here. Second area is government procurement. Governments buy lots of iron and steel. Governments buy lots of cement. If governments had standards for those products that were related to their carbon content, to the carbon life cycle carbon content, that could drive a lot of innovation. It could drive a lot of opportunities for offtake of low carbon iron, steel, and cement and related products. This is an area that's got huge potential. There's buy clean statutes in California and some other states that could be models for legislation in this area, actually federally and then around the world. Fiscal subsidies are an obvious opportunity. Always attractive to give tax cuts and tax cuts for industries that invest in this area. Subsidies of different kinds, including subsidized financing, including direct funding, could all help to move this agenda forward. Mandates as well could tell industries to do this, tell industries to hit specific standards, on the model of our environmental legislation, and we could mandate best available technologies in this space, and then ask industries to hit the standards that have been developed by regulatory agencies. Infrastructure development is really important. Some of this agenda will require the construction of new pipelines. If we're going to do electrification on a large scale, it's going to require huge investment in transmission infrastructure. So governments will have a very important role to play in infrastructure development in connection with this. This carbon prices and carbon tariffs is an interesting question here. Many of the industries that are involved here are energy-intensive, trade-exposed industries, and they tend to have been exempted from the carbon pricing schemes that have been implemented worldwide. I think there's interesting questions about the extent to which carbon pricing can make an important difference here from a political economy standpoint. But then also there's a risk of leakage if there's carbon pricing in this area, unless there's a robust system of carbon tariffs to prevent that leakage. It's a very interesting topic. We can get into that in question and answer period, but potentially an important tool here, but others may be more important for addressing this part of the climate problem. Industry associations could be very important. Having a global network of industry, for example, iron and steel industries working together would avoid some of the leakage problems. You could also imagine treaties, sectoral treaties, where countries come together and commit on a sectoral basis that their iron and steel or cement industries or related industries will adopt certain reforms. A little bit on a Montreal Protocol type model. There's some lessons to be learned from the Montreal Protocol experience there. And then the Clean Energy Ministerial offers a great platform for addressing these issues. Actually, just in Paris earlier this week, talking with the Clean Energy Ministerial team at the International Energy Agency, which is interested in this, and is looking to try to jumpstart some work within that platform on these issues. So those were 8 ideas. We're sure there are more, but we hope this gets the dialogue moving beyond where it is right now. This is the roadmap, so here's our roadmap, and it's a visualization tool for everything we've been talking about. I won't pause on it here, but if you're interested, go take a look. This kind of sums up everything that we've just been talking about. And so, as Julio was highlighting, this is an area in which there is strikingly little scholarship and in which much more is needed. And in our we're running short on time, so I'm just going to go through, I'll quickly pull these bullets up, but on systems analysis, we need more work on techno-economic analysis, and on policy designs. All of this is really important. And so to sum up, here are our key messages. Important, challenging problem with much more work needed. Hope you've gotten a quick sense of that from this presentation. 4 technology pathways, which we looked at, hydrogen, biomass, electrification, and CCUS. RD&D is essential. Many policy options are available, and government procurement's a particularly powerful tool. This work was done in connection with a conference that happens every year in Tokyo called the Innovation for Cool Earth Forum. METI and NIDO have helped to sponsor this work. We thank them for their support in generating in this roadmap. And with that, thanks to all the co-authors who contributed. Thanks for coming, and we'll turn it over to Colin. Take it from here.
Okay, thank you, David. And I believe we have the executive summary of the report, copies of that out front, and also the slides are up on our event website. So now we're going to turn it over to 2 people that we've invited to provide their comment and their perspectives on the report and some of the findings. First is Aaron Burns. Oh, well, actually, no. First is okay. Aaron Burns, Director of Policy at Carbon 180, which is a climate think tank that focuses on carbon removal.
Thanks so much. Yeah, so we focus on all things carbon removal. We work on natural and technological solutions as well as related areas. So things like carbon tech, which is the term that we use for products that can be created using that captured carbon dioxide. Broad industrial decarbonization is really important and a focus of our work at Carbon 180. We cover that from a handful of different perspectives. I know Jesse is going to cover carbon capture in more detail, but I did want to say we are very strong supporters of carbon capture, especially in the industrial sector. I want to touch on the opportunity to support industrial decarbonization through carbon tech, which Julio kind of briefly touched on, in particular with building materials, as well as some of the policy pathways that we think are going to be especially important in this area. So carbon tech is, again, the term we use for when you take that carbon captured either through ambient air, through direct air capture, or through point sources and carbon capture. And it can be used in the creation of building materials and other products that can displace higher intensity incumbents. And there are companies out there doing this today. Julio mentioned both CarbonCure and Solidia. They create commercial materials that you can go out and purchase today. I think CarbonCure has upwards of 80 locations you can go buy these today in North America alone. And one of the most compelling things for us about carbon tech building materials isn't just the emissions reduction opportunity, but they are commercially competitive, not just available, but commercially competitive today, and that there's an enormous economic opportunity. So 2 former colleagues of mine, Matt Lucas and Rory Jacobson, did a market sizing report. It's available on our website, and looked at the total available market for carbon tech goods. And in the US, they found that that total available market is around $1 trillion. That includes building materials, but also fuels and other chemicals, plastics. And that number is closer to 6 trillion globally. So there's an enormous opportunity there. And we talk a lot about why we need to decarbonize industry, and that's really important. But we also see a really big opportunity within that challenge. So I think carbon tech in particular can help kind of clarify that opportunity. So we can imagine places where we create low carbon steel using carbon capture, use that captured carbon dioxide to create other low carbon products, and that we do that all in a way that centers communities, labor unions, other key constituencies to fully realize both not just the climate benefits, but also the economic benefits. But all of that, as both Julio and David have pointed out, is really going to require a lot of policy. Luckily, we're starting to see a little bit more policy action come out of the Hill on industrial decarbonization. So right now in the Senate energy package, there are two bills in particular, or versions of two bills in particular I wanted to highlight. One is the EFFECT Act, which also has a House companion. This is really focused on updating how the Department of Energy does its carbon capture R&D. And relevant to this discussion, I think, are two really important points. One is that it includes industrial carbon capture for the first time in the authorization. Historically, the carbon capture R&D at the Department of Energy has been really focused on the power sector and in particular on coal. So this would broaden that to include industrial capture specifically. It also expands the carbon tech work. So in the carbon use program at the Department of Energy, they've been doing a lot of really fantastic work, but it's a program that's had a relatively low amount of funding, $10 to $12 million a year. And this would up that amount of money. I will say overall, I think another really important thing that this bill does is to provide additional funding across the board for carbon capture. The other bill I want to highlight, a version of which is also in the Senate energy package and is also bicameral, is the Clean Industrial Technologies Act. So this is a bill that would require the Department of Energy in coordination with OSTP to establish a new advisory council, coordinate funding for developing innovative technologies, and really take a kind of integrated cross-agency approach to industrial decarbonization around research and demonstration for these projects. So both really important bills. The other thing I wanted to mention that we've seen, we are in the middle of the appropriation season right now for FY21. Last year, we saw a couple of really great things. We saw more funding for industrial, like dedicated funding for industrial carbon capture at the Office of Fossil Energy. That was the first time I think we ever saw dedicated set aside money for industrial capture. We saw an increase. I mentioned carbon use has historically been funded at about $10 to $12 million. We saw nearly a doubling of that last year. And I think a lot of us in the room and others in DC are spending a lot of time working with appropriators to see what we can do this year as well as they work on authorizations through the Senate energy package. And then I want to touch on, the report really goes into more detail on some of the important policy pathways, some of them existing, and I think there's an opportunity to look at new policy pathways as well. So ensuring financing mechanisms like loan guarantees, master limited partnerships, and others are available and workable for industrial carbon capture projects or industrial decarbonization projects. This is funding that's available now. These are mechanisms that are out there. These are relatively easy policy solutions. As David mentioned, infrastructure, I think especially when we're thinking about deploying these technologies in the early stage, is going to be incredibly important and take a really strong federal and state role. And then procurement can be another key opportunity on all of these pieces. So federal and state procurement, the report mentions the California Buy Clean legislation, but as David alluded, there are other states looking at this, New York, Hawaii. There are efforts that other organizations have been undertaking here in DC to figure out what are the ways that we can learn from things like California Buy Clean, apply those pieces federally. Finally, I just want to say, I think certainly in this space, we talk a lot about the pathways, the policy levers that are already out there today. That's really important. I think that's a really a reasonable first step. But I wanted to point out that I think we're also in a really exciting time for climate legislation. We have big proposals like the Green New Deal. We have the Clean Future Act. We have all of these ideas and enthusiasm for big climate legislation that goes beyond just these existing policy levers. And so I think today in particular, we have an opportunity not just to support industrial decarbonization through those existing policy levers, but also be really ambitious and creative to look for additional and new policy pathways that are going to help us reach the industrial decarbonization as quickly as possible. And with that, I'll hand it over to Jesse.
Jesse?
Thanks, Erin. That's a great setup for my remarks, and thanks to Aspen Institute and ITIF for having us here today. I'm Jessie Stolark. I'm with the Carbon Capture Coalition. I'm the Public Policy and Member Relations Manager for the coalition. And before I obviously I'm going to talk a lot about carbon capture today and kind of talk about what the Carbon Capture Coalition is doing to see the next commercialization of new projects come online. But I wanted to take a step back first and kind of underscore this challenge. And I'm going to give you my favorite statistic on the building sector, which is by 2060, the world will double its building stock. And that's like building one new New York City every month for the next 40 years. So in the United States, we're largely in a cycle of maintenance in terms of our infrastructure. So this is really a challenge for the developing world as well. So if the global demand for steel is set to increase 30% by mid-century, and the demand for cement will increase by 12%. So that's just kind of underscore, and I don't have the statistic on the top of my head, off the top of my head for chemicals, but those are also set to demand will increase significantly as well. So just kind of underscoring the challenge and how we really need an all-hands-on-deck approach here, especially for the industrial sector. If you aren't familiar with the Carbon Capture Coalition, we are convened by the Great Plains Institute. And we are a coalition. We have 76 members. Many of our members are in the room here today, or out here speaking with me this afternoon. But we support three things in terms of commercializing carbon capture. The first is emissions reductions. The second is supporting domestic energy production. And the third is to protect and expand a high-wage job space. So we bring a really diverse coalition to bear on federal policy around carbon capture and climate policy. We're fond of saying that you can come to the table for different reasons, so long as you see commercialization of carbon capture is a really crucial piece in the overall economy. And so that's sort of who we are. And if you're interested in learning more kind of about our policy platform, we do have a policy blueprint that was published last year that outlines kind of our policy initiatives. And I would say that after the passage of 45Q, we have gone from looking, really focused on the passage of 45Q to kind of looking at this whole ecosystem that, previous speakers have talked about in terms of commercializing the sector. So in terms of carbon capture in the industrial sector, I think there is a lot of near-term opportunity. We are already seeing carbon capture projects come online in some of those pure stream sources that were already talked about, like ethanol, ammonia, natural gas processing. And I think 45Q will certainly be a driver there in the near term. And then if we look, in terms of lower purity industrial streams like cement, petrochemicals, and steel, I think, what we're seeing is that there is tremendous interest, and the interest is really ramped up since the passage of 45Q. We have, demonstration projects coming online all over the globe, and we have a new, it was just announced, I think, in the last couple of months, a demonstration project in Colorado on a cement facility for carbon capture. But, obviously demonstration and commercialization are two separate things. And so what are, the Carbon Capture Coalition is looking at some near-term policy opportunities that we think are going to be really critical to advancing the sector. So within 45Q, we're looking at two things. The first is extending the commence construction deadline. So we have a very narrow window here. We were given 6 years when the legislation was first passed, but we lost 2 years because IRS hadn't issued guidance for over 2 years for part of that. So that's the first one, is to extend this commence construction deadline, because it's nearly impossible to if you're going to be a project developer starting looking at a project today, to say that you're going to begin construction in 4 years. And then the second, I think, is really interesting, and particularly from industrial, and also when you start to look at utilization, is the threshold. So 45Q has thresholds that you need to meet in order to receive the credit. And for industrial applications, that's 25,000 tons of capture. But if you talk to people in the industrial space, they're going to do as much capture as they can, but they might not be able to meet that threshold initially. So we actually see that as a huge barrier to innovation. And then the third thing I would say is we are also looking at financing mechanisms, and there are bills that have been introduced in this Congress, both on direct pay and enhanced transferability, and just structuring financial mechanisms around the tax credit to allow greater flexibility for project developers. And we're really, in many ways, looking at what has been afforded to other zero emissions technologies like wind and solar, and thinking through what is the beneficial ecosystem that those technologies have been able to access, and what does that look like for carbon capture. And then I just wanted to close and talk a little bit more about why the 4-year window for commenced construction is so untenable, essentially. If you look at putting together a project for carbon capture, you have to do a FEED study, front-end engineering design study, and that's sort of basically penciling out the project at the facility level. And that takes a minimum, I've heard it takes a minimum of about 2 years. And then you also need to apply for, if you're doing geological storage or saline storage, you need to do a Class 6 well application with EPA. There's one project currently injecting in a saline formation, and that's ADM's Decatur, Illinois ethanol facility, and that project took them 5 years to receive their Class 6 well permit. That was the first project to receive a Class 6 well, so we could anticipate, we could see lower the time frame go down. But if you start to add up these time frames for all this together, you're already outside the commenced construction window. So it's critically important, and that's really, I would say, kind of our number one legislative priority at the moment. We are very lucky to have some great champions on Capitol Hill. There was actually, on the energy package that was just introduced, a friendly amendment to expand the commenced construction window, or extend it, by 5 years, led by Senator Capito. It's a bipartisan amendment. And then there's other, proposals out there that whether it's 1 year or seeking permanence for 45Q tax credits, but this conversation around commenced construction is ongoing. But I'm really interested in hearing from my fellow panelists and all of you, so I'll end there.
Okay, so I will kick us off with a few questions for the panelists. Also, I want to point out we're welcoming Colin McCormick to join the discussion, one of the other report authors. Colin McCormick has previously consulted for ICEF on carbon utilization and direct air capture, and also WRI on carbon removal. But so I'll kick us off with a few questions. If you're watching online, again, you can submit your question. Just tweet at us with the hashtag ITIF Clean Energy. But first, I guess for really all of the panelists, one of the really exciting things going on right now on the Hill this week is the Murkowski-Manchin American Energy Innovation Act, which would be the first big reauthorization of Department of Energy R&D programs since, was it EPAC 2005 or EISA of 2007? Aaron, you mentioned some of the provisions for the industrial sector. How well do the recommendations of the report map onto the industrial provisions of this act?
I would say, I think that the bills that are being considered are a good first step. There was a big emphasis in the report on R&D. Again, I think the two bills I would point out are the ones, that we had mentioned earlier. One is, we need R&D at the Department of Energy on industrial carbon capture. As Julio kind of repeatedly emphasized, carbon capture is a super important opportunity in industrial decarbonization. And the way that we've structured, when we're looking at EPACT and the last authorization of the Office of Fossil Energy, a lot of that has been focused just on power sector, just on coal. And there's been a pretty concerted effort over the past few years from a bunch of folks, including many members of the Carbon Capture Coalition, to expand that authorization and for the Office of Fossil Energy to include industrial capture in that. And I think we were really excited to see in the FY20 final appropriations bill at the end of last year, dedicated funding, I think it was about $4 million, so a small amount of funding, but a good start on dedicated to industrial capture. And I think expanding the work that the national labs, DOE do on this, really, really important. I think one of the things that's most compelling about the other bill we mentioned, the Clean Industrial Technologies Act, is that it does include carbon capture, it includes the Office of Fossil Energy, but it's a much broader look at industrial decarbonization, including the Advanced Manufacturing Office and EERE, other agencies outside of DOE, that we're looking at OSTP level coordination so that it's not just one piece, one technology pathway like we're talking about in the Office of Fossil Energy. It's looking at all of these pieces, and more importantly, I think, we're thinking about DOE overall, how all of those pieces fit together. So I think that they're really great first steps on the R&D, and I think we're really excited to see that shift where I think a lot of us in the carbon capture world, in the deep decarbonization world, have been thinking about the industrial sector for several years. And that hadn't necessarily been reflected in legislation. And so I think it's especially exciting to not just see these bills to see these bills introduced, but to see them be bicameral, bipartisan, and to see them actually have a chance at being enacted.
And Julio?
Two quick additions to that. I don't believe this is in the bill. I hope I'm wrong and it is in the bill, and I hope that if it isn't, that someone would consider this friendly amendment. Data and analysis. Data and analysis. We discovered as we were going through this that ammonia production data is managed by the United States Geological Survey because ammonia is considered a mineral resource. I don't know why, but that gives you a sense of just how difficult it is to even just find the data, much less mine it for information, much less aggregate it, much less anything else. That just pulling this data together on industrial heat and industrial production would be a great function, and there isn't a government agency that's doing it well now. Along those lines, the analytical tools to use that data don't exist. If somebody were to say, well, how big a transmission line would you need to decarbonize the Gulf? We could not answer that question today. We just couldn't. How many miles of pipeline? What are the trade-offs for cost? We don't have answers to this because we don't have tools because nobody's doing the work. So in addition to the data gathering function, it would be good for this bill or to include something that tasks offices to understand and integrate that stuff. This gets to the second point. This is brief, mercifully short. This silo busting function is incredibly valuable. The Department of Energy is right now organized along fuel lines. That's not necessarily the most propitious way to go about doing this. Secretary Moniz, when he was at the DOE, did a lot of work exploring this to try to figure out if there was another way to reimagine the Department of Energy by breaking the silos and thinking functionally instead. I certainly hope that that's something that's worth considering as well.
So to the data point, one thing that was included in the Senate Appropriations Committee report last year was direction to AMO to do decarbonization roadmaps for different sectors. So hopefully AMO will do those roadmaps, and that can provide some of the data that would help. But sort of building on this R&D, okay, if the first step is authorizing new research programs focused on the industrial sector and focused on the application of some of these technologies to these different sectors, if authorization is the first step, the next step is appropriations. We have to pay for it. So if you're telling appropriators, how much do we need to do R&D in some of this space if we're not doing any of it or very little of it now? For everyone.
I'll leave the exact numbers up to the authors of the report, but I will say, in CETA, in the Clean Industrial Technology Act, we had seen in the bills that were introduced about $500 million a year authorized. Right now, the carbon capture program with Office of Fossil Energy gets about $100-ish million, 117 we might be at for FY20, $117 million a year. The industrial carbon capture set aside last year was $4 million. So I would say a lot more is the number. And the authorization, I will say, again, one of the things that's important in the EFFECT Act is that it does raise the overall authorization for the Office of Fossil Energy. I think there's been really broad support for this sort of thing. We've seen amendments since 2015 in the original Murkowski Energy Bill in committee to expand the amount of funding that the Office of Fossil Energy gets for carbon capture. You've seen industry groups, climate NGOs, everybody kind of really rally around that. And I think particularly around industrial decarbonization, that there's going to be a lot of broad support on and off the Hill for more money for that. And so I do think that barring some, there's obviously a larger budget environment that we have to be thoughtful about on the Hill, but that we have seen over the past few years funding increases for general energy innovation, lots of those keeping us even close to on track for emission innovation funding levels. So I do think that there's a bit of momentum to be taken advantage of here, but I would say, yeah, just a lot more money for industrial decarbonization.
Go ahead.
So in looking at CO2 removal as a topic, the National Academy's recommended about $600 million a year for a research budget for the engineered pathways. The Energy Futures Initiative did their own analysis of this, and they came up with about $1 billion a year for the engineered pathways. The challenge that we're looking at here is at least commensurate and equal to that size and scale. You should be thinking on the order of a few $100 million to $1 billion a year as the opening entry. It's important to note that a certain amount of that is for demonstrations farther out. It doesn't necessarily all start at the beginning, but by 2023 we should be thinking about mounting pilots and demonstrations of these, which costs actual money.
I want to mention really quickly, just on a slight note of hope, is that the first year for direct air capture in the National Academy's report was about $60 million a year. Last year in appropriations, we got $60 million for negative emissions technologies, with a big chunk of that towards direct air capture. So it's a big challenge, but I want to say I think Congress is interested in trying to get there.
And this needs to be a global effort. It's good to be talking about the federal budget here, but we need research and development agencies around the world to be paying attention. This needs to be part of mission innovation.
I'm going to put a plug in for, Julio mentioned the need for data collection. By and large, that's not free, but it's cheaper than a lot of the other stuff we're talking about. So as you look at sort of a supply curve of what would be cheap to buy versus what would be expensive to buy in an R&D agenda, let's make sure the data is really looked at carefully on that.
So on that topic, the three of the technology solutions that was explored in the report were still combustion-based, either CCS, post-combustion capture, or modifying combustion to use biomass or hydrogen. The electrification strikes me as a completely different kind of approach that would require completely new plant and process redesign. Are we doing any research? Is anyone doing any research in, say, electrified ammonia production?
Well, I'll say a few words on this. So we see more in Europe on this, particularly balancing the grid and using variable renewables. You look then at whether you can integrate the grid with industrial production in an intelligent way. We haven't seen as much of that in the U.S. I would love to see it. It does require getting different parts of DOE to work together well, and it does require looking at what the consequences to grid operators would be.
There is a little bit of this going on. Almost none of it's federally funded. There's a little bit of this in the Office of Fossil Energy, actually in EERE, on things like synthetic fuels or synthetic chemicals made from CO2 by reverse fuel cells, by basically electrocatalytic processes. And you can do something like that. It's all early days. It's a few $million right now. In contrast, say the Breakthrough Energy Ventures people have put a bunch of money into Boston Metals, which is a direct ore processing through electrolysis pathway. Their budget equals about what the Department of Energy's budget is right now. And the same thing is happening for companies who have invested, say, in Opus 12, or companies like BASF. Like, there's a lot of money in the private sector that's going into this. But still, we need demand pull for there to really be private money coming into this. The private money is small because the markets are immature. So, in fact, to get more R&D done, the government procurement lever ends up being important. If you can start even a very thin wedge of procurement for things like plastics made of CO2 or fuels made of CO2 using electrical pathways, then that will actually stimulate more investment in that.
Okay, so begin getting your questions ready. I'm going to ask one more question. On hydrogen, it's been the focus of previous cycles of hype, and I'm thinking the focus on fuel cell electric vehicles during the early Bush administration. What makes this time different?
Let me start with that provocative question. The real issue here, the clarifying concept, is carbon. Hydrogen isn't really an energy technology. It's a decarbonization pathway. It's a clean fuel. It's a different thing. And when the idea was, well, we can just make more energy this way, or we can have a particular energy pathway, it was hard to justify. When zero's the number, which the 1.5 degree report's been pretty clear about, when zero's the number, you start going back and saying, okay, well, we have to think about the hard stuff now. What can we think about? And hydrogen's particularly important for three actually hard sectors. One of those is shipping. We just don't know how to get shipping. We just don't have good answers. But one of the interesting pathways is ammonia, which is basically hydrogen. And about half the ships in the world could run on ammonia today. So if you could make enough ammonia, you could do something about that. Second is heavy-duty vehicles. Very hard to electrify, especially long-haul trucks and stuff like that. It's just very hard to electrify, so hydrogen looks like an important option. And the third is this, industrial heat. We haven't really thought about that. That was not part of the conversation in 2002. It's absolutely part of the conversation now.
Yeah, I think there's an open question about whether it will be different. I mean, there are some sectors, and Julio just enumerated them, where we need hydrogen. But unless we produce it, you know, as green hydrogen or blue hydrogen, it's going to be bad from a carbon standpoint. And so it is absolutely essential that as we scale up end uses for hydrogen, we also scale up clean production of hydrogen, or else we're going to be going backwards with this technology.
And I'd add, I think, you know, as all of this needs policy, it just takes time and education. You're talking about the Bush administration looking at this, but 45Q took 7 years, you know, and 5 years ago, as a congressional staffer, Senate staffer, meeting with our executive director, Noah, about direct air capture and hearing about it for the first time. Now we've got $60 million. Like, I think that this is, unfortunately, this is just a kind of a function of how congressional policy works. Staff has, you know, not a ton of time. It takes time for us to go in and educate them, for this to be a priority. And so I think that with things like with CETA and other bills like this, I think that there's a reason to be hopeful that this time is going to stick a little bit more.
Okay, can I answer my own question too? One thing that I also think sometimes gets overlooked is that regardless of future applications in energy systems, we produce hydrogen on a large scale now, and we use it for ammonia production for fertilizer. And that demand is going to go up. So even if we don't use hydrogen in energy systems, which, I mean, based on your report, it does look like it's the most promising alternative for some of these sectors, we still need to decarbonize hydrogen production just for current uses.
That's true.
Right, but I'll go back to one of our findings, like straight up, if you're making low carbon hydrogen today, which you can do, it still costs twice what natural gas costs. If you're running a big petrochemical plant, your question is, how do I get my money back? How do I avoid losing market share to somebody in Singapore who's not paying that price? And this is actually, again, part of the nature of this has to be an international discussion about how you manage these trade issues. And there's nothing simple or easy about that. It's going to take a lot of time to resolve.
Okay, on that note, I think let's take some questions from the audience. Ed? Oh, and I think we've got a microphone coming around. Go ahead and say your name and where you're from.
Okay, first I'll say thanks for the panel. I found that very interesting. I'm Ed Ryder from ACEEE. Most of the solutions that you enumerated were singular solutions. I wanted to ask if there has been an analysis across the board looking at a systems approach. In an industrial sector, for example, chemicals or refining, they could use not only electrification for heat, but they could also use hydrogen, they could use CCS. Efficiency could play a role in all of those solutions. How do you see optimizing the cost, reducing the hurdles, using a systems approach?
Look, I'll start with a few things. So you've mentioned electrification. I guess that's why I end up being answering partly. So there have been some analyses, but very, very few. I think we are a little bit constrained by policy options to think through this sort of thing. It's always easier through policy efforts to be a little bit piecemeal on this. We do see, so unit level, the Boiler Mac rule, looking at ways of pushing unit efficiency or unit transition through policy tools we know how to do. Systems level transitions are much harder to incentivize through policy. So that's maybe a macro answer. Have we seen these analyses? In some cases, they can be very grid specific. So the characteristics of my electric grid will very much influence how I want to think about electrification. And then finally, these are very heterogeneous processes, and it does require think Julio, well, many of us bear scars of the siloification within government of thinking about this stuff. That level of systems analysis would require a whole lot of different expertise if done internally to government, and that's often hard to get done. So maybe I'll put that there, and I know other people want to.
Yeah, well, and there's no question that efficiency is an important part of the solution here, and that recycling and coming up with ways to make sure that we're optimally designing products so that they can be reused. It's going to be part of the decarbonization agenda. This report had a different focus. We looked at how do you decarbonize the remaining processes for heat production once you've gone through all that. So that's what we look at here.
Two other quick things on that. Three, really quick. First of all, is a shout out to our co-author, Roger Ains, who is not here. All through the report, Roger was bludging us and saying, hey, there's trade-offs, we need to think about the system stuff. And there's quite a lot of that in our report. I would encourage you to take a look in terms of the discussion. The second is a point that we made. We don't actually have good tools to do that systems analysis today. They don't exist. So an important undertaking is actually to build these things. And then the third point is we decided early on that we were not going to do any optimization. That is a good thing for master's students to do for the next 20 years. That's not a good thing for us to do now. And instead, we should focus on what we can do first, because once we start doing things, it'll be opportunities to figure out how to improve and intensify as we go forward.
Okay, up front.
Thank you. Thanks for a great panel. I'm Barbara Tyron, and I have a question for David. Yesterday at Resources for the Future, former Secretary Moniz talked about these issues a little more broadly, but generally energy technology and climate change. And he cited the importance of coalitions, coalition building, as he put it, writ large. Energy companies, financial institutions, environmental NGOs, all coming together to make this happen, because that's the kind of breakthrough momentum that will be required. As you're talking about your policy options, do you have any comments on that?
Oh, wait, anything Ernie says is always right. It's a hugely important point. And this doesn't work without building the coalitions that will propel this through the U.S. Congress and this town and the same all over the world. But I think this is an area that's rich with potential for that. I think you can see putting together coalitions involving those who are focused on climate issues, involving workers, involving industries, involving broad collections of countries with different interests, and that it's going to be absolutely essential.
Yeah, and I just wanted to add to that, the Carbon Capture Coalition is incredibly diverse in our membership, and I think that's what makes it unique and what really has helped in terms of elevating the carbon capture as an issue. It's U.S. focused, but we draw from labor unions, fossil energy producers, the three largest conservation organizations in the United States, energy and environmental nonprofit organizations, technology providers. So it's kind of amazing to watch this group kind of come together. There are individuals in the group and organizations that don't agree on a lot of things outside of carbon capture, but they all agree that carbon capture is an essential tool. And so, when you give that list of members to a congressional office, it does make them say, oh, interesting. It's really interesting what you guys are bringing to the table. And I think to that point, I think what has happened with the negative emissions technologies and direct air capture is phenomenal. And that's, again, an example of a huge, broad coalition, and industry needs that. That doesn't exist yet, I don't think. If it does, please let me know. But, it doesn't exist to bring those policies to bear at the federal level, and it's definitely needed.
Energy policy has been unhealthily dominated by physicists for generations here. So my question is just I'll ask this question of a known physicist on the panel, I guess, but looking through I haven't read your entire report, obviously, but there's one huge area of innovation that doesn't seem to be here, and that's synthetic biology, biological innovation. And after all, if we want to make cement at sea level, ask an oyster. And so the question is, there seem to be enormous opportunities for using biological means for innovation, certainly in industrial processes, industrial products.
So let me just talk a little bit about that as a geologist, not as a physicist, and not as a biologist. First of all, biomimetic pathways and biological pathways remain really deeply interesting. And if you're thinking about new projects and new pathways, the innovation pathways should explore those for real. I will say that, and of course, innovations like CRISPR make this all the more interesting. There may be ways to think about really, hacking the genome of a whole bunch of species and coming up with good stuff. It is also possible to generate materials that are biologically inspired, like catalysts based on enzymes that can do a bunch of the work using biological templates. The substrates that microbes use, their physical substrate and surface, ends up being reactive territory that's very useful. That said, the viability of a lot of this stuff in practice has proven pretty hard to get. It turns out that life seeks its own equilibrium, and that often is pretty far outside of what an industrialist seeks. It's hard to actually make organisms do things they weren't made to do, and it's hard to make new organisms, period. And so I think it's absolutely worth pursuing and exploring, and Lord knows we've put nowhere near the money into it that we need to get going. But we've been humbled by stuff like cellulosic ethanol, where we basically lost 10 years of research and the biologists threw up their hands and said, we were wrong about a bunch of stuff, we got to start over. And I think we have to be humble in the face of that in terms of what we think we can do.
Well, and maybe I'll add a comment. Nice to see you, Henry. I think we did look at biomass, and you do look at the tools of synthetic biology to improve yields there. We see that in improvements to photosynthesis that you can engineer into a number of crops. But that seems aligned with other goals of increasing yields that doesn't necessarily need to be called out specifically in this context. So absolutely fantastic tool, not speaking as an expert, but we didn't want to focus on that specifically in this context.
Robert Margolis from NREL. Robert Margolis from NREL. One of the numbers that we have been kicking around for the U.S. is that 2/3 of industrial process heat is at below 300 degrees C. And you jumped in the U.S. It's a different mix globally, certainly, but a very large percent is low temperature. And you jumped right into the need for very high temperatures. And I think this gets back to this question of more of a systems perspective of there are a broader set of technologies that could feed those lower temperatures. So how have you thought about that in terms of the mix of different temperatures in industry?
It's a great question. So I'll say we had predicated the entire analysis on, yes, there are wonderful technologies to provide sort of 200 C in that range heat. We didn't think that needed as much attention. So what we thought was less clear in the landscape was what do you do about the higher temperature, high quality heat that you really can't get with a heat pump. Maybe you can hit with concentrating solar, maybe. But we felt that the really hard nut to crack was way up there at 1,000 C, which is very relevant and very real in these industries. So not to say those aren't important questions about the lower quality, lower temperature heat provision, but we felt there was a bigger bag of solutions available.
I do want to add one quick thing, though, and that's shout out to NREL. We've told you over and over again there's not a lot of scholarship out there. One of the places where we found really great scholarship on this topic was NREL. They published a whole series of reports on low carbon heat and potential for hydrogen and potential for nuclear and all these other things. And they did a bunch of joint reports with INL. I would encourage people to go find that stuff. There's a treasure trove of data and information.
I'm actually going to ask a follow-up. Heliogen received a lot of press towards the end of last year for announcing that they had achieved, I think it was 1,000 degrees Celsius using concentrated solar power?
1,500.
1,500, okay, even higher. Your report didn't look at concentrated solar power. What's your assessment of it?
Well, we did look at concentrated solar power. And some of those were comments that David made at the beginning. There's a geographic mismatch. 60% of heavy industry in the United States is in the Gulf Coast. You can't use solar concentrating power there. And we're not going to dislocate all of those industries and move them to the Atacama Desert. Like, it's just, like, that's, some aspects of that are not realistic. And I have a lot of time for Bill Gross, and what he's accomplished with Heliogen is actually pretty remarkable. The thing that's most remarkable about that is not the temperature, but the fact that he insists he can get the temperatures for about a quarter of the price of a concentrating solar plant, which is noteworthy. That said, so far he has shot that heat onto a cinder block. He hasn't actually, made that into workable heat that does a thing. So there is certainly more challenges to that. He's going to keep getting more money. They're going to keep trying stuff and scaling up. I'm not trying to minimize the accomplishment, but that is still not the same thing as heat that does work.
And I'm sorry, I want to add one more comment, which is we have to think about transportation as well. You can move electricity, you can move natural gas, you can move hydrogen. You can't move high temperature heat. We bumped into this issue about thermal storage repeatedly. And that should be part of a larger, broader agenda in the industrial sector and energy technology more broadly. How can we buffer and store particularly high quality heat in a much more efficient way?
Jim Sang, I'm a retired physicist. This follows up on the last question. I knew a lot of crystal growers, and what I learned from them was 300 or 400 degrees is trivial. Growing a crystal at 1,000 degrees is not too bad. Silica is usually done. Do europium chalcogenide or rare earths and it's 1,500 degrees. That's hard work. Is there a simple metric for what a convenient temperature is? I.e., is there something we can aim at to lower your 1,600? What would be the benefit of lowering, for example, Dr. Stanilow pointed out that glass is 1,600 degrees. If you do glass at 1,200 degrees, what kind of savings would that get you?
Right. So the challenge of this is that the core physics and chemistry doesn't happen at lower temperatures. Period. There's not an efficiency you can get. I started by saying you're burning rocks to melt rocks. The recipe for glass is you melt sand and pour it on liquid tin. There's not a lot that you can do about the heat budget associated with that because you're starting by melting sand.
But I remember some of my people were trying to grow glass were casting glasses from polymers, I guess, or something like that. It never went anywhere. That was 20 years ago.
So there's a lot of great research to be done in advanced catalysts, in very different processes, in materials substitution. Fantastic. We really wanted to keep this grounded as much as possible in current processes, relatively easy retrofittable technologies, things that an industrial plant owner could look at and say, I can see that coming down the pike. I don't have to believe in 10 miracles, or I don't have to wait for 20 years. So that was the constraint. Not to say there isn't grain R&D to be done. But we were trying to operate in a nearer term. Yeah.
Randolph, do we have any questions online? Nope. Okay. Then, yes, over here.
Richard Coleman, just a retiree. You say there's not much research, but you think of countries that are less opposed to the climate change acknowledgement, Japan, Germany, and those are industrial steel makers that have been ahead of us for decades. Do they not have something on the table that we can piggyback on?
No. We actually looked at that pretty hard. It's not like we didn't have the internet. Like, we searched high and low, and there were a handful of pilots, and there were a bunch of papers that were sort of out there. But there isn't a big, industrial decarbonization pathway research program in Japan. There's a hydrogen program in Japan, and so they were like, hey, can we put hydrogen in a steel mill? Let's try that. They did that, but there isn't, in fact, this sort of broadband decarbonization focus in heavy industry in those places either. It's worth knowing, by the way, that even in climate acknowledging countries, as you refer to them, most heavy industry have a climate waiver. Most of them, by law, are exempted from carbon budgets and carbon taxes. That's begun to change. So in the Netherlands, for example, everybody takes a 30% haircut by 2030. Everybody. All sectors, all industry. Denmark has said they're going to decarbonize 70% by 2050 or 2040. And again, everybody's caught up in that. But they made those promises before they built a research agenda around it. And so the people who we've talked to in those countries are more enthusiastic about replacement pathways. So, for example, Sweden is doing a fully electrolytic steel mill where they use green electrolysis to make hydrogen and run hydrogen through a DRI process. And the Swedish steel company SSAB announced earlier this month that they were going to replace their asset base by 2040. But that's not research. There was no research involved. They're just doing electrolysis to make hydrogen and running it through a DRI plant. So even in those contexts, we found there was surprisingly little out there.
And just to add really quickly to that, if you actually look at the global flow of carbon or embodied carbon that, is embodied in all the goods, that whether we import them from China or we're exporting them, if you include those in global climate goals, we completely blow the budget. So this is something that the United States is on the same page as everybody else on this one.
Cheerful thought. I think there's a question in the back.
I thought it was Joe. Yeah.
Thank you. Joe Heiser from Energy Futures Initiative. I thank you for the report. It's very interesting, and I certainly agree with you on your innovation recommendations. The question I have on that point is that if you are recommending a large increase in public investment in R&D in the industrial sector, how would you propose to deal with the issue of intellectual property, particularly if you are, cost sharing some innovation with a particular company in a particular industry? How are you going to deal then with the issue of either competition or technology diffusion, particularly when you have public money involved along with private money? I wonder if you could comment on that.
Happy to take the first shot at that. It is an important question. We do have decades of experience, though, I think, through DOE programs on how to handle this issue. And we, of course, have Bayh-Dole and Stevenson-Weidler to set policy on this. So broadly speaking, I think we would recommend borrowing and using the same sorts of approaches that are used in renewable power and other sectors where we've seen technology development that's cost shared by DOE. So it is competitive. That's true, but this isn't really the first time we've bumped into that exact same problem. I think broadly, Bayh-Dole and Stevenson-Weidler would govern the sort of legal technicalities of that, and then the management challenges around that. I think DOE has shown itself generally able. I'll be interested if there are disagreements, but generally able to handle those kinds of sensitivities in other industries.
Yeah, it's an important question. It's not one that we looked at in this report. I would even throw that back to you, Joe. I'd actually value your thoughts on this now or later. But I think it's a really important question. It's a tough one. Yeah. But Colin's exactly right. We've dealt with this through DOE, through Bayh-Dole and some other mechanisms over the years, with some success, some failures. I think we need to build on that in this context.
Now, just as a quick comment, there's a difficult trade-off. On the one hand, you want to encourage innovation by allowing the innovators to hold on to the intellectual property, but on the other hand, in order to get decarbonization at scale, you need widespread diffusion.
And I think we've got time for one more question over here.
Hi, I'm Omkar Khandekar. I'm an MBA candidate at Georgetown University. So I was wondering, what is the impact of the plastic and that particular industry on the carbon footprint in terms of both upstream production and then downstream in terms of disposal?
So I don't have deep numbers on this, and I'm sure that things I'm about to say are off by a bit, but I think they're directionally correct. The total volume of plastics produced every year is on the order of 1 billion tons. So it's actually pretty small from a carbon footprint perspective on the basis of things, as opposed to, say, fuels, which are 10 times bigger than that. It also means that there are pretty hard limits on how much CO2 you can put into plastics. From a carbon tech perspective, it's just you can't get more than a couple of 100 million tons at best and probably less than that. Even the biodegradation of plastics doesn't contribute substantively from a greenhouse gas perspective. It's one of the things that I find problematic in our discussion because people often conflate plastic pollution with climate questions. We saw that, for example, in the series of town halls that CNN did with the candidates on climate change. About a third of the questions were on plastic pollution, were not immediately relevant to climate change. And in people's minds, they often think of these things identically or as closely coupled. I don't believe that's to be true.
Okay, let's wrap up. I want to thank everyone for joining us, and thank you all for coming here.
Glad you made it.
Why doesn't anybody mention our CCUS study? Why didn't anyone mention our CCUS study? We both got rising costs.